nice time, and it's nice to see so many of you here. I'm going to present a paper called Safe Wrappers and Sane Policies for Self-Protecting JavaScript. And it's a joint work with Fufung and David Sands. And it's a continuation of their work on the lightweight self-protecting JavaScript. So lightweight self-protecting JavaScript is an approach to mitigate cross-site scripting by giving, so I'll briefly explain it. So we have a number of built-ins in the browser, and the window object points to those built-in methods. So what their approach is to use aspect-oriented programming techniques to wrap the built-ins. So you create wrappers that will enforce some policy before executing the built-in, and redirect the pointer to the wrapper instead of to the built-in directly. So whenever we try to execute alert, what we will actually execute is the wrapper, which will then, if the policy agrees with it, execute the built-in. And the main point here is that the wrapper will hold a unique reference to the built-in. So even though a malicious application or a cross-site scripting attempt redirects the reference to alert to a malicious alert, they still won't be able to obtain the functionality because it can't get access to the reference inside the wrapper. So we have behavioral sandboxing, in the sense that the behavior of the browser is sandboxed rather than, for example, the DOM tree or something like that. And we only wrap built-ins because they are the foundations upon which the user scripts are built. So they provide the functionality to user script, and if it's wrapped, or if we can control the behavior, then we can mitigate whatever code is executing, we can control it. So, and this is, it has to be executed the first thing. So the wrapper has to be, or the built-ins has to be wrapped the first thing, because as soon as user code executes, we really do not have any control over what happens to the environment that's we're going to wrap. So it could be redirected to a malicious alert before we wrap, and then we will have lost the whole point of wrapping. So as long as we make sure that it executes the first thing that happens in the page load, then we can control the behavior. And this is lightweight in the sense that we don't need to analyze the code. We don't need to transform the code. We just make sure everything's wrapped, and then we have control. So the library, so the lightweight self-protecting JavaScript consists of a wrapping library that provides the functionality of wrapping built-ins, and some policies which enforce the behavior. And the policy code is site-specific, so we can have multiple, or we will have different policies for different sites. One site might allow alert to be executed 5 times, and another site might not care at all about if alert is executed or not. So when I started looking at this wrapping library and these policies, I found some some attacks, both actually on the wrapping library itself, how it performed the wrapping, and in the policy code, or some problems that affect the policy code. That is basically what the paper is about, and what I will be presenting today. So when it comes to the wrapper, 3 types of attacks were found. And together we have discussed and came up with solutions to these attacks. So the first one, function and object subversion. So a function instance, for example, or any object actually, will inherit from its prototype chain. So a call to apply of a function will actually look up the prototype chain until it finds apply and execute that apply method. But if we modify that apply, then we also modify the behavior, how it behaves for the function instance. And that is something that is accessible to the user code after wrapping the function itself. So what we found was that at one place in the wrapper code we had ran apply on the original function, on the original built-in. So by modifying the prototype of the function object, so redirecting the apply function to mean something else, then we could capture the original built-in as it was executed. So a fix for this is simply to make sure that the original apply is actually the original apply function that we were expecting in the beginning, the unmodified version. Another problem, global setter subversion. So we have a function closure, and inside this closure we have a variable. We create an object and assign it to a variable. And this is supposed to be inaccessible from the outside. It's supposed to be contained inside the function scope and not be able to leak outside. But in some browsers, we have global setters. So we can define a setter that will be in effect for every object, and especially it will be executed upon instantiation of objects. So when we actually create this object over here, the setter will be executed, and we can steal the secret. In the wrapping code, at one point, we created a temporary object just to pass to the policy, which contained the original built-in. And by defining this setter for a field in that object, then you could steal the original built-in back. So one way of fixing the wrapper would be to not allow a temporary object, which might work in the wrapper code, yes. We can make sure that we don't create any temporary objects. We pass all the arguments as is and so on. But maybe in general it's not feasible. Another way would be to use safe objects, objects that do not inherit from any setters or so on. And I'll talk more about safe objects later on. And the third possibility would be to change JavaScript to not execute setters upon instantiation. And that is actually what has happened in Firefox. They do no longer execute any setters upon object instantiation. however, Chrome and Safari still does. Another problem is an aliasing problem. So we have a built-in, the actual built-in somewhere inside the browser, but we have a number of different aliases for this built-in. And one of them will be passed to the wrapping code, to the library, and it might be that you just wrap that particular alias for this function. But what you actually want is to wrap the function itself. So regardless of which alias you use, so you will still use the, it will still point to the wrapped object, the wrapped built-in, or to the wrapper. Another problem with aliases is dynamic aliases. So aliases that is created dynamically. And so, for example, in one browser, alert points to the built-in alert, and we add a wrapper to that and point it to the wrapper instead. Perfectly fine, but the malicious code in this page might create a new window which has its own pointer to the built-in, and then reassign alert to actually to the other window object's alert function, and restore the functionality that way. So these are all vulnerabilities or problems with wrapping or with the wrapper. Dealing with this problem is actually quite hard. And so far, the only solution that we've found, even though we've been working on it for quite some time and we have some ideas, but the only solution so far is actually to not allow access to any other window object. So when it comes to policies, in fact, we have the same problem for policies when it comes to function and object subversion, but it's even worse. So for a policy, policies we cannot control. The wrapper we can control. We know what the code will be. We know what will be, what we can, how we can write a good wrapper so that it's not affected by this. But the policies come from the policy writer. So someone else is writing the policies who might not know about these problems. So we need to write our wrapper in such a way that it allows the policy writer to use as much functionality as possible without having to know, in a safe way, without having to know all the vulnerabilities. So for example, in the policy, if we have a whitelist, which consists of an object where a domain name is associated with true if it's in the whitelist, and we do a lookup in the whitelist, if it's in the whitelist, then it's okay to be visited or something like that. Then it can be subverted by, for example, creating a global, so a property that is associated with all objects, and that will be inherited by the whitelist, so that evil.com is also included in the whitelist. And another way, in this case, since we are using a built-in function, we can actually reassign the function to mean one thing when it's accessed in the whitelist, and when it's actually later on used in the code, then it will return something else. So one fix for this would be to use the has local property. But again, that's something that the policy writer would have to know. So he should not